Okay, let's continue with the IIR stuff. So, let's first start with the, let's see, I'll close the windows. There, closes all the windows. Okay. So earlier we had this notch filter. Maybe I should take a picture of that one and then draw something there. So if you have made a spectral analysis and find out, okay, there is a funny peak at the middle of it and you want to get rid of it, maybe some interference noise from some source. This band stop notch filter is then a good solution. So basically, if your notch frequency is, let's see, Fn, you first design the filter on a complex plane, adding zeros on that angle which correspond to that Fn. So sampling rate I have 44.1 kilohertz. So okay, for example, I could use 5 kilohertz. Yeah, I have some filters there, so we can actually take a look at those later on. So let's put that noise frequency at 5,000 hertz. Or interference. Of course, in real life, you would do a spectrum analysis and then find where your noise is. But now I just said it, okay, it's 5,000 hertz. The corresponding normalized angle would be omega n is 2 times pi times Fn divided by Fs. So it's linearly proportional to the to this Fn, and that's the scaling factor is basically 2 pi divided by Fs. Quite obvious. This is 2 pi is equal for the sampling rate Fs. So that omega n it would be on that angle. And yeah. So this is the normalized frequency in radians. Good. And now we set the zeros on that angle. So first the first zero, and on the unit circle, J times omega n. There. So that's 1 0, but actually we have to have both a plus and minus angle there. So basically the complex conjugate. We can do it also this way. J and minus J. So it gives the angle on both directions here. Both. That way J times omega is here and minus J times omega is there. There, good. And now we can even plot these zeros. But let me put poles also for a moment. So that's just currently in the origo. So this would actually define a FIR system. Since we need, in addition to zeros, we also need the poles. And then Z-plane, ZZPP. Ha! There you are. So those are the locations of the poles. How come they are so close to that picture? Beats me. And by the way, the center pole is a double pole. It just doesn't show it. Okay, next step would be to calculate the corresponding polynomial coefficients. So the B are the polynomial coefficients defined by zeros. So filter coefficients. So this is the numerator coefficients, and AA. Well, that will actually become just 1, but I will just do it like this. So if we have double 0 at the origo, it will actually give you 1, 0, 0 as the polynomial coefficients. Did it do that? Yeah. So AA equals 1, 0, 0, meaning this is FIR system. Okay, and now we can actually calculate the frequency response on a new figure. Ha! There you go. So evidently it actually does some good attenuation at 5 kilohertz, but it has awful passband characteristics. So now we actually put the poles in here. And we are not arbitrarily putting poles, but we can also define what is our band width. So basically, we can also set the half band parameter, which is the minus 3 dB width for this filter, and for in this case, let's use 100 hertz. Sounds just about as good as, well, let's put it 200 hertz. It looks better on display. Of course, this how wide do you want that filter depends, of course, on the application where it's going to. How accurately at 5 kilohertz you actually have always that notch, or is it moving a little bit? Narrower you make your filter, less it has actually a tolerance against small changes on the frequency. And sometimes you may need to make an adaptive filter to do the filtering, meaning a filter that measures the frequency and then tunes the notch accordingly. But well, this still, that's a good start. So 3 dB half width, or would it be more or less minus 3 dB half width? HW half width would be, I said 200 hertz, right? So 200 divided by Fs times 2 times pi. So this is actually also translated into this normalized frequency. There. And that defines the range from unit circle. And it also defines the 3 dB half width. Same distance. So we can actually then calculate the poles. Poles are on the same angle. So I'm now taking my poles from Origo and move them to correct locations, meaning that the range from Origo would be 1 minus HW, and then multiplied by the zeros. Yeah. So the zeros were on the unit circle. So if you multiply by a new range, then you'll get something like that. Let's put this one on the first figure. So now, okay, there we go. So we are quite close to the unit circle here. That's the 200 hertz distance. So basically we have the 200 from 200 hertz to 200 hertz here, a notch. All right. So we'll see what next. Okay. So next step would be to just calculate again the coefficients. So BB actually, we didn't touch the zeros. This remained the same. But AA, we calculate again. So feedback coefficients change, and previously those were basically 1, 0, 0, and now AA equals 1 minus 1.4705, 0.94, something like that. And let's check what it looks like. Ta-da! So seeing is believing. Now at the 5 kilohertz, we have a notch with a width of 400 hertz. The full width is 400 hertz. And I just used the complex plane to design that filter. Okay, now you know how to get rid of one part of one signal frequency on data. Good. Next, let's find out how to design other IIR filters. So-called classic IIR filter designs are Butterworth, Chebyshev, and that's the first type, Chebyshev, and elliptic. And there's Bessel also. All of these have a different kind of generating algorithms, but let's take a quick look at the first one, there is actually a Butterworth filter design function is called butter. Good. So generate a Butterworth filter. Default is a discrete space filter. That's nice. You can also actually design the uh, uh, continuous time space filters, so analog filters. A little bit heavy tool for that. There are much better tools online, for example. But anyways, it takes the width, no, yeah, well, the order number n, and then cutoff is actually pi times omega radians. So we need to do some adjusting for real uh, what is that? Real filters. So basically, if you put there 0.5, it is so that's our Nyquist rate. It's basically this one is normalized to 1. So you need to calculate if you have a cutoff frequency of, for example, that let's make it, for example, 1 kilohertz cutoff frequency. Then you need to adjust that one into, 1 divided by Nyquist rate over 2. Yeah. Wait. So that's how this function works. And it gives me directly, let's make it BBA and BB2, AA2. For example, a fourth order Butterworth design for cutoff frequency, did I say 1 kilohertz? Divided by Fs over 2, or Nyquist rate. There. There we have. So, yeah, looks like that. So it starts, the cutoff frequency is it at 1 kilohertz? Maybe. Let me mark it 5 so we can actually check it. Hard to say otherwise. Yep. So 5 kilohertz cutoff frequency, and then it starts to go down like that. Okay, again, the scaling is kind of funny here. But what can we do? Options. Does it have any? No. What else we could do is calculate the frequency response. BB2, AA2, H8, and then go figure. And now I can do the axis. There you go. A little bit too much. But anyway, so we have 5 kilohertz cutoff frequency for Butterworth design, and Butterworth was optimally flat on the passband. And then this actually, that part depends on the order number. So let's take a quick look if I change the order number. Fourth order or eighth order. Then I calculate the frequency response again and do the figure and some axis for that one. Okay, so fourth order filter and compared to eighth order filter. Okay, so more you take these or more you have the stages there, better attenuation you will get. There must be also a better way to define a filter. Since remember the box. Box actually had the ripple, cutoff frequency, and also the transition bandwidth and attenuation. So that's spot here. How to otherwise than to just by a trial and error to find the correct correct order number. Well, one easy way, 2 stages means 20 dB per octave. Oh no, 20 dB per decade, more attenuation. Okay, the same way as analog filters. So basically it's 20 dB when you add stages to the system. But anyways, let's do it the better way. So there's also a function called boot_ord, like order number of Butterworth. Compute the minimum filter order of a Butterworth filter with the desired response characteristics. The filter frequency band, blah, 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 blah. Okay, frequencies are normalized to the Nyquist frequency, and RP is the allowable passband ripple in measurement, and RS is the minimum attenuation in the stop band, also in the decibels. So we need to put there WP is passband frequency, and then WS is the stop frequency, RP is the ripple. For Butterworth, that actually is minus 3 dB point, or you can also define minus 2 dB, but minus 3 dB would be the perfect one. Then the stop band attenuation. So yes, you actually define that box. So you have WP, WS. This here actually is with, if this is 0, that's the RP, and this one here is RS. So design box. And let's try that one. So our order number, ON, that's not good. Or Orden is boot_ord. For example, now we have the 5 kilohertz again divided by Fs/2. Okay. Then stop band start frequency we could put, for example, at 7 kilohertz, 7,000 divided by Fs/2. Then minus 3 dB design point. Let's see, ripple. Minimum attenuation. They are called talking about attenuation. So in this case, it should be actually a positive number. The gain would be negative attenuation. Let's use without a sign. So that means minus 3 dB point. 3 decibel ripple. And also attenuation. It's positive number when it attenuates. Gain would be negative decibels. Remember this relative kind of things. So let's find the order number for a filter that at 7 kilohertz we would have 60 dB attenuation. So 5 kilohertz FS on 7 kilohertz, 3 dB ripple, and 60 dB attenuation. All right, what did we get? Where's my order? Order 19. Ha! Okay, good. I have number 19 there. Excellent. So now I can go and design the filter. Instead of that, I will just put 19. Bang. Calculate this. The frequency response, and then plot that one. Ha! And at 7 kilohertz, which is somewhere here, we have at least that 60 dB attenuation. It doesn't matter if that goes to, well, practically to infinity. See, minus 500 dB is a lot. So, well, actually, look at that one. It hit the floating point accuracy level here. So machine epsilon is found. So, but anyways, that's in reality that will go to 0, which means infinite decibels there. But anyways, that's what happens when you warp the frequency scale by grabbing from infinity and minus infinity. There on the blob. But anyways, this is the way to design a low-pass Butterworth filter. How to design high-pass and band-pass? Well, quite similar way to, just a moment. Let's take a look at the Butterworth filter design program. You can also actually just select that one to high-pass filter. So low-pass, high-pass, band-pass. So we are lower and higher cutoff frequency, and band-stop. One single function gives all of those. You don't need to worry about the modulation. You can modulate though, but then you need to modulate both the numerator and denominator separately. So that's possible. It still does the same effect. So think of a system which is FIR. If you modulate just this numerator, it does something for the 0 points. It just moves them on different place. Same thing actually if you have poles here. If you modulate, it moves them also around that modulation frequency. So practically actually, well, this band pass and band stop and high pass, they are just doing the modulation there. Okay, and the same thing here actually, that you need to still find out the order number from the transition bandwidth requirement, or transition bandwidth and attenuation requirement. So basically, come to think of it, the whole box needs only that corner and that corner. So you have a pair of the stop and start frequency and attenuation factor. And then you have this cutoff frequency and where that is defined at the ripple level. Good. So this way you can go and design these IIR filters. And in addition to the Butterworth, we also have the Chebyshev filter design. I think Chebyshev 1 is the function call. Yes, Chebyshev 1, Chebyshev type 1 filter. And also we have the elliptic. Ellip. Yes. Boy, I'm good to remember. Somehow just remembered. So elliptic filter, and there are also some others. If we had the octave, yes, SourceForge project sites are currently under maintenance. So sorry about that. We cannot get the online help at the moment. It looks like they may be under the network attack. If you see any of your friends doing network attacks, go and beat them for me, right? So just take an ugly stick and beat the hell out of that person. That's so stupid. Especially that kind of facilities like SourceForge. It's basically engineers are there, the computer scientist engineers are providing really good stuff for free. And then there are some jerks that go and start sabotaging that one. For what? My question is. Okay, now you know what to do with the hackers. Good. So let me take a quick look on exercises at the end. Was there any special things more? No, I don't see anything. Okay, so basically the last, if you have several filters and you want to basically combine these, the easiest way to combine those results would be, okay, let's go to Octave. I have few filters there. Let's see, I have this BBAA filter. I have also some HHWW filters. So if you have several signals and you want to generate, let's see, let's do something here. Okay, 2 second long and SS. Note C. Ah, okay. 440. SSN. That just generates a little bit of noise here, nothing more serious. So that actually have a spectrogram of looking like that. Okay, that's dull and boring. Maybe I should have changed that one. Well, that's just fine. So that was just a sound sample for me. it's a 440 hertz monotonic sound. But if I want to basically combine different filters, as on that the very last exercise, you just do filtering with each of those filters separately and then combine the values, output values. So for example, I have a low pass filter, the latest one. I can filter BB, AA, and then that SSN. Okay, that's a low pass filtered. And then I have had some high pass filter also somewhere. Filter HHWW high pass. That was filter. That was the FIR filter, and maybe I also could incorporate that. Do I still have it, or did I? AA and BB. Do I still have the notch filter somewhere? Maybe not. Okay, BB, AA. That's the notch filter parameters. I can actually even do the filtering for the notch filter. That was on BB, AA, and then this is N. And then combine these with the different gains. Say SSLP times 2 plus SSHP times 3 plus SSHP NO notch. Let's what happens? Okay. Oh no, did I break this? Oh shoot, I broke the program now. Oh, okay. But anyways, you just add those with the gains. Okay. So let me finish up with this one. So there are different ways you can combine those filters depending. And the easiest way is just to either cascade the filters, or then in this particular case, actually, I have the combination of filters and then all right, say just the cam. Okay, so in this the 5.10 exercise, you have the high pass, middle pass, low pass filters. Each of those have individual gains, which are given in dB. Okay, that would be there. And then you just add the outputs together. That's not a biggie. Okay. If you need to basically another kind of filtering, so you are filtering the cascading filters. For example, that the bandpass filter, or if you want the notch filter combined with bandpass filter. Notch convoluted with bandpass filter. Bandpass filter BPF. The easiest way is actually put the bandpass filter first and then the notch filter second, that way. So signal to one filter first and then to the other. You can also mathematically calculate the total filter, but it doesn't have any, say, it doesn't help you. Okay, so those are the ways. Final hint for this, I think I have it there for the fourth exercise. Okay, yes, I have it. The fourth exercise, there's that voice sample what I have there, the mystery language. And when you are trying to hear what this talk about, so a couple of things. Use headphones, then you get much better voice reception. And then power up if necessary. That voice sample has a lot of noise and it's scaled down. So if you just filter everything, you still cannot hear much. So basically turn up the volume. And how to turn up the volume? Well, in Octave, you just multiply it with the 10 or 100 or something like that. It's just multiply the value. Good. Wow. So that was my show for today and for this trip. So just remember, well, let's see, a couple of things. So first thing to remember is to remember these deadlines. I have marked that now the deadlines there. So the first exercise deadline is this week Friday. Everyone has already returned that one. Excellent. That's still one. I have given comments, and there is still one mistake which can be still fixed. So I have a comment on that mistake, and then I will be just marking the returns there probably, since you will get the comments by email. I think you get the announcement when I'm commenting your sheet, right? So check the comments, what I'm actually telling there or hinting what could be corrected. Otherwise, well, it has been really fun experiment for me to teach you. So I would be really so glad to come again here to teach more of that stuff, and hope to see you in Finland someday. Remember summer in Finland, especially August. 20 to 25 C, nice breeze of air, 20 hours of sunlight. Yeah, do I need to speak more? Maybe not. Okay, but anyways, thank you very much for your attention.